Mr. Chairperson. It's my great pleasure to give a talk. And first of all, I would like to thank all the organizers, especially Professor Che and Professor Lee and Professor Kim. Maybe my pronunciation is not so good, Kim. And also, I thank all the local organizers for making a perfect preparations for the transportation from Tokyo to Seoul and from to here, and everything was very, very nice to me. And once again, thank you very much all the local organizers. And indeed, I'm very happy to give a talk about the microphone. I think it works. Yes. Okay. And the topics are maybe to somebody a bit exotic. Namely, main object is not partial differential equations, but like a partial differential equation, fractional diffusion equation. Then maybe it can be interpreted by parabolic equations and elliptic equations. And I hope that my topic is within the scope of this conference. Okay. Then there are several physical motivations or backgrounds. Then please, please let me speak a bit naive figure. Mainly, as one physical background, we are considering the diffusion of the contaminants under the ground. Of course, this is a very serious problem in many situations. Well, contaminants might be some industrial throw away poisonous material, and very unfortunately, recently, of course, this is related to the radioactive substance after the catastrophe the last year in Japan. But the point is that we would like to make a better prediction of the diffusion of the contaminants. Then the first issue is that we must consider the soil. Then soil is highly heterogeneous, not so homogeneous. Therefore, in one word, we must consider anomalous diffusion in the porous media. The second point is that the scale is quite big, maybe a few kilometers. Therefore, there are many mathematical models. Then, for example, typically it's a nonlinear Laplacian, like a porous media equation. But here, especially related to some macroscopic models used by environmental scientists, I would like to propose to use so-called fractional diffusion equation. Okay. Then the next is just the repeat of the physical background. Then our task is some mathematical treatment or analytical treatment or quantitative treatment for the anomalous diffusion in heterogeneous media such as soil. Then although there are other classical and quite well-known model equations, however, we would like to use the fractional diffusion equations like that. And immediately later, I will explain this, but for the moment, you can please understand symbolically. This is like a alpha times derivative. Usually, alpha is between 0 and 1, and this can be one good macroscopic model for slow diffusion, especially in the big field. Okay, then one typical anomalous, one character of anomalous diffusion is that slow diffusion, or long-tailed profile in time t. Then roughly, this is sorry, I did not define so correctly, so accurately the solution. But please understand roughly that U is a solution. U satisfies fractional diffusion equation. Although I did not define so clearly, but anyway, U satisfies some fractional diffusion equation. Then usual decay rate. One can prove that the decay rate is more or less t minus alpha. Then, of course, the classical diffusion equation shows the decay with exponential rate. Therefore, this is more or less slow diffusion. Then, this is very, very naive numerical computations. Alpha equal 1 is like a classical diffusion. Then, alpha equal 1/2 now we are considering 1/2 time derivative. Then, of course, this is very, very fast or rapid diffusion. This is the x-axis. This is, of course, the time. Then if alpha is between 0 and 1, for example, 1/2, the diffusion is not so high, and still t equal 10. Yeah, 10 has, of course, no special sense, but 10 is not small compared with 1. Then still some part remains. Of course, when we consider diffusion of contaminants, this is a very dangerous situation, because near the source term, still after many times, unfavorable material or something, or such as contaminants, remains. Therefore, we should find more suitable governing equation for better prediction of the danger. This is a main physical motivation. Okay. Then from the mathematical viewpoints, within this time, I would like to speak about some inverse problems. Maybe inverse problem is not the main subject of this conference, but however, maybe please let me speak about that. Then, for the moment, I plan to explain several inverse problems, backward problems in time t, and unique continuation, and some determination of important physical parameters, and so on, so on. Okay. Then, from the technical or mathematical viewpoint, those inverse problems are already have been studied classically and quite well to the classical parabolic equation. Therefore, my motivation is very naive. I would like to copy, or I would like to trace, or I would like to repeat some researches for various kind of inverse problems already done for the heat equation. Of course, heat equation or parabolic equation is not same as the fractional diffusion equation. Then some part is same, but other part is completely different. Okay, I mentioned. Okay, this is like a motivation. And before going to the technical part, please let me make some short deviation. Namely, at first I should define, Then, so far I did not define so clearly about the fractional derivative. Then, we will consider the following so-called fractional diffusion equation. Then alpha is a non-natural number. Then let us assume that alpha is between n is a natural number, between n minus 1 and n. Then we will consider like that, and minus a is a classical uniform elliptic operator. Then in this case, we will consider only t direction fractional derivative. Then what is the fractional derivative? And indeed, the history of the fractional derivative is quite old. In some documents, one can say that Gottfried Wilhelm Leibniz has written some note to Marquis de l'Hôpital in 1695, more than 300 years ago. He mentioned that the derivative of power 1/2. And also after that, maybe you know that there is a very famous paper by Abel treating Abel's integral equation. This is like a minus half derivative. This means that 1/2 integration. Therefore, I would say that fractional derivative itself is not a new concept. Then, naturally, there are many variants of the definitions like that. But here, we will adopt the following definition. This is a definition of the fractional derivative with order alpha. Of course, depending on interpolating natural number alpha, we must take suitable time derivative. But simplest case that alpha, let us assume alpha is between 0 and 1, which we will mainly consider. Then this case n equal 1. Then this means that one time derivative. And if n equal 1, this is minus alpha. then t minus tau over minus alpha multiplied, then integration. Then one can very, very naively count the number of the derivatives or integration. Then here is one differentiation. Then here is 1 minus alpha integration. Then after subtraction, formally speaking, we can understand that this corresponds to the alpha times derivative. Then sometimes this is called the fractional derivative in the Caputo sense. Caputo is an Italian, I think, engineer. Caputo is a bit complicated in the German-speaking country, but because not broken down. Caputo is the name of the Italian researcher. Okay. Then this is a definition. Then again, mainly we will consider this kind of equation. Then by some physical modeling, sometimes we should consider multiple time fractional derivatives. But at first, we will consider a single case, namely only alpha time derivative, alpha time fractional derivative. And for the moment, for the special part, we will not consider fractional derivative. Okay, then indeed, a bit more from the intuitively, I would like to explain about that fractional derivative in time t. Naturally, of course, alpha equals 1, then this is nothing but the first time, one time derivative. Therefore, this is so-called local operator. But if alpha is non-integer, definitely this is involved by integration in time t, so-called memory effect. Therefore, this derivative, the equation, fractional diffusion equation, has not strong smoothing property. And if one can immediately remind that alpha equals 1 corresponds to the parabolic equation, then parabolic equation has a very strong smoothing property. But however, in our case, some memory term, then strong smoothing property is, say, modified, not so strong smoothing property. But however, in a sense, of course, this is not at all mathematical statement. In a sense, the propagation speed is infinite. This is a very rough aspect. This is, of course, like a character of the fractional derivative itself. But however, of course, this will influence seriously about the result of the inverse problems if we compare the inverse problems with the inverse problem to parabolic equation. This is quite natural. Okay. Then, although I will not touch the direct problem to the fractional diffusion equation, still there are many spaces for further researches for the direct problem, namely inverse boundary value problem. Then roughly the character is as follows. This is very rough statement. Intermediate between the parabolic and hyperbolic. Not very strong smoothing property, but in propagation speed, in a sense, so-called infinite. Then almost same thing for the parabolic case is as follows. First of all, if we consider non-homogeneous term, then if we consider the regularity of the solution within the Helder space in time t, a very corresponding result to the parabolic equation, like by means of the analytic semigroup theory, can be proved. Then maximum principle is proved, but not like a strong type, weak maximum principle. And that part is not yet well studied, but some parts for nonlinear dynamical system can be done. Like the stability stability where the linearized equation has only stable eigenvalues and so on. Okay. Then then from the first page, this problem itself has been motivated by a bit more practical situation. Therefore, I'd like to give just one short glance of currently executed some comprehensive projects. I am one of the members. Then Of course, there are very nice mathematical problems. Then approaches like me based on the basis of the partial differential equations or like evolution equations. Other thing is that since the medium itself is like heterogeneous, therefore there is definitely one very hopeful approach, that consideration by means of the fractal theory. Indeed, there is some the collaboration with Professor Kumagaya at the Kyoto University. He is a specialist for the fractal, the diffusion of the fractal. Also, other things that this is very natural consequence. Multi-scale modeling is very important. And also, yesterday, Dr. Pozao gave us some talk about the Helleshoff problem homogenization. Then definitely this has close relation. Also, definitely the engineering aspect is very important, but just a keyword is that the risk management after the catastrophe, then definitely environmental science. And definitely from the side of the industry, this is a very important subject, because in the manufacturing processes, there are many, many heterogeneous diffusions, how to control, how to predict, how to optimize, and so on. Therefore, for the moment, we have this kind of somehow comprehensive interdisciplinary research project. Then maybe I am permitted to give just a short announcement. Sorry, this is not related to the mathematical part. One engine for such project is that we are organizing every year twice a study group, so-called study group for solving industrial problems. Then this is very roughly speaking, giving actual working place by industry and mathematics. The next is in January, and if you are more interested, please contact me. Still, just fixed the participating companies about 3 days ago. Therefore, the homepage is not prepared. Anyway, this is like interdisciplinary working spaces. Anyway, then now mathematics. Okay. Then at first, as a mathematical topic, I would like to speak about the backward problem in time t. Then backward problem in time t is, in a sense, very classical inverse problem, especially for the heat equation. And the backward problem is that, like that. Oh, sorry. This is just the first page, in a sense, gives everything to my results. Of course, this is not my result, but the backward problem for the heat equation, very bad, because heat equation is not reducible. One cannot go back to the process. The process cannot be returned. Therefore, after increasement of the entropy, the reconstruction of the initial value from the present time is very, very unstable. In other words, severely ill-posed. On the other hand, alpha equal 2, if you remember the notation, alpha equal 2 means that wave equation. Maybe some, can I shift up? Do you think? We got it. Okay. Maybe in some minutes up, then you can see. Or you cannot see finally. This is not my business anyway. Okay, alpha equal 2, our equation is a wave equation. Therefore, for the wave equation, backward problem is just the same as the forward problem. Then perfectly well posed. Then my result is that if alpha is not integer, not natural number, then moderately ill-posed problem. Moderately ill-posed or well-posed. What is the sense? Then this is a first result at my talk. Then let us assume that alpha is between 0 and 1. Then we will consider like that. Minus a, simplest case is that minus a is always Laplacian. This is just one simple case. Then, okay, maybe I will write down. This is a definition. Gamma is, of course, gamma function. This is just for your reminder. This is a definition. If alpha is between 0 and 1, that. Okay. Maybe not so clear, but nothing is better, worse than something. Okay. Then the result is as follows. Okay, capital T is positive number. Then at time T, we know the state of the solution for x direction. Then we'd like to determine ux0 by means a1x. For the moment, for simplicity, we are considering Dirichlet homogeneous, the homogeneous Dirichlet boundary condition. Then, okay, we need some regularity, but the like H2 for final value. Then we can prove that initial L2 norm of initial value is equivalent of H2 norm at capital T. Then this also, this is both-sided estimate. Then, moreover, this means this theorem means that solvability. Therefore, for any given A1 from this class, there exists a unique initial value such that the solution takes this value at capital T. But however, we must change. We must take a bit stronger norm H2. Therefore, this is the sense that the moderately ill-posed. Not L2 to L2, but L2, H2, everything is okay. Then this is a case of between 0 and 1. What happens alpha is between 1 and 2. And from the environmental viewpoint, usually alpha is between 0 and 1. But just other thing that if one will consider the propagation or diffusion in the air, usually better model is that alpha is between 1 and 2. This is super diffusion sometimes called. But anyway, this is like a mathematical completeness. If alpha is between 1 and 2, this is the same. Then in this case, we must consider as initial conditions two kind of conditions, namely like u itself and the first derivative of time t, because alpha is bigger than 1. Then the pair of initial values are estimated by that. This is the combination of the norms itself are same. H2 at capital T is equivalent initial L2 norm at t equals 0. Then that part was proved by Professor Ito at the North Carolina State University and my previous graduate student. Now he works at Nippon Sumitomo Steel. Very recently the name was changed, sorry. Okay, then next is, okay, this is a backward problem. Backward problem means that we know boundary condition perfectly. This is like boundary condition we know, but we don't know initial value. But we know some final value. Then we'd like to determine initial value. And on the other hand, unique continuation is also in the PDEs theory very classical problem. Namely, we don't know boundary condition perfectly. Then simple case that one special dimensional case, we know only one boundary condition. But however, this point also we have the data of the flux. Then here is like a zeroth order and the first order, like a Cauchy data. Then how much we can determine the solution itself. Then this is a unique continuation. Then that part is joint work with Jijun Liu and Lian Yang at the Southeast University in Nanjing in China. Then our case, unique continuation can be stated as follows. Always capital Q is like a cylindrical domain. Omega is a spatial domain, and 0 to capital T a time interval. Then we will consider this kind of fractional diffusion equation in the cylindrical domain. Then gamma is some sub-boundary, suitable sub-boundary of the spatial domain. Then on this lateral sub-boundary over time interval, we will assume that Cauchy data or Dirichlet and the Neumann data Dirichlet and Neumann data are 0. Then can we conclude that some subdomain D where U vanishes? Then this is a very classical formulation of the unique continuation. Then this is a very classical case, namely alpha equal 1. Then unique continuation for the parabolic equation is quite well known. Namely, the answer is yes. And any sub-boundary gamma, this is correct. This is like a typical parabolicity. Then the technique, several techniques, but the one typical technique is that some L2 weighted estimate, which estimate is uniform with large parameters. This is so-called Kalema estimate. Then something like a tool, typical tool. Then the proof of the Kalema estimate is usually done by integration by parts. Okay, then when we will make imitation for this technique, unfortunately, immediately this technique does not work. Because for Kalema estimate, integration by parts is very important. Integration by parts very important, although this is very elementary. Namely, main difference from alpha equal 1, integration by parts fails for the fractional derivative. And also this has some memory effect. Therefore, expected unique continuation cannot be same, because this is a Cauchy data. Then, okay, t equals 0. Then definitely the effect of initial value cannot be neglected. Thanks to the memory effect. Still, this is an open problem, no counter example, but something very different. Okay, then this is one very naive, maybe too simple case, but the one unique continuation. Namely, this is a very special case, 1/2. 1/2 is not alpha, this is nothing but only one case. Then also one-dimensional case. Namely, Q is like an interval. Then this is like a Cauchy data at x equals 0. Then Cauchy data vanishes. Then if we could have this conclusion, then everything would be same for the Parabolic. But unfortunately, we must assume that initial value is given. Say for the unique continuation, without loss of generality, we can assume that initial value is 0. Then indeed, this might be very essential. In other words, one cannot omit this condition. But at this moment, I'm not so sure, because as I said that, no counter example. Maybe you can have better idea. Then this is first very simple result for the unique continuation. Then this is only the uniqueness, but if Cauchy data are not 0 and initial value are not 0, then however we can prove some stability with some boundedness assumption. This is so-called conditional stability. Then the key is, this is a bit contradiction, but however, Kalema estimate. Kalema estimate, L2 weighted estimate. Then usually if I will touch the Kalema estimate during my talk, this is usually to the majority of the audience, this is nothing but a nightmare, because many equalities, very direct inequalities. Therefore, I will skip. But the point is that 1/2 is very special. Namely, let us consider very naively. This is not, indeed, the following naive consideration is not perfectly correct, but can be justified. Namely, this is 1/2. Then 1/2 derivative and one more 1/2. Then maybe one can get one-time derivative. Then, okay, then let us operate 1/2 derivative. Then here is just one time. Then this is like a 1/2 plus 2. Then this means that fourth order equation. Then maybe somebody is quite familiar with Kuramoto-Shibashinsky equation. This is the first derivative in t plus fourth order. But here is first order in time t minus fourth order. Therefore, a bit strange, but don't mind, because usually after taking one more derivative, we must take care some additional term. Therefore, no contradiction, because t first order minus fourth order means that no solution, because every mode is exponentially growing up. But this is of course completely different problem. Then this is a key idea. Therefore, definitely 1/2 is very necessary. Okay. And we need an initial condition and also one-dimensional case. For proving the Kalem estimate, then for the moment, no Kalem estimate for general alpha. Of course, one can prove the Kalem estimate if alpha is 1 over integer. But this is, of course, a bit complicated. Anyway, I will not touch. Then, okay. Then other unique continuation is that. Sorry. Then okay, maybe 10 minutes. Okay, but this is like a relativity. This means that 10. Okay, 10 minutes. Okay. Then, this case is like okay. Then this is a bit okay. Then for simplicity, let us assume that ft equals 0. Then this is like that, and still initial condition is necessary. Then omega is sub-interval we will fix. Then we would like to determine other part of the boundary data by means of this data. This is other kind of unique continuation. Okay, for the moment, for saving the time, maybe please neglect that. Without that, we can get the conclusion. Then the conclusion is that if f equals 0, then we have very good Lipschitz stability. H is observation data of the interior domain. Then if one point is given, boundary data is 0, then another point of the boundary data is estimated by interior data. Then quickly, if we consider one-dimensional heat equation, this is absolutely impossible because heat equation has very strong smoothing property. Therefore, omega is far away from the endpoints. Therefore, we cannot control at all L2 norm. We cannot control by L2 norm of interior value by the boundary data. But however, in the fractional case, we can prove like that. Then even if alpha is between 1/2 and 1, we can prove that unconditional Lipschitz stability, namely both sides. Then this is like one case of the interpretation that fractional diffusion equation is intermediate of the parabolic equation and the hyperbolic equation. Okay, maybe I should skip. Then other inverse problem is quite pretty. This is not very the proof is rather direct and primitive, maybe high school level or undergraduate level. Namely, like that, two derivatives. Then I will not touch, but from the engineering viewpoint, how to estimate alpha and beta. This is very, very important. Then from the microscopic model, alpha and beta correspond to the power of the Poisson distribution. This corresponds to the generalized random walk, but I will skip that part. But finally, in the macroscopic model like that, main issue is that how to determine alpha and beta. The inverse problem is that take one observation point. Then this is a point-wise observational profile of the density. Then we'd like to determine two exponents. Then the answer is very simple. Yes, we can determine both uniquely. Then next is that what happens multiple times may be correct. That part is still under the work. The other thing is that this is only that part I'd like to touch is the fractional derivative in x direction. Then this case very naively a is like a minus Laplacian. Then that case is a simultaneous determination alpha and gamma. Then answer is that if we choose suitably, namely initial value is non-negative or non-positive, then the uniqueness is okay. This is much more important in the engineering simulation case. Okay, anyway. Okay, then I think okay, maybe shortly touch. That part is by Jin Chen and Junichi Nakagawa from Nippon Steel, and myself and my previous student. Namely, determination of one derivative order and plus coefficient. Because in the previous section, I just mentioned that only the determination of alpha and beta or something. Then the point is that from the theoretical viewpoint, interest is that one observation at one fixed point over time interval can contain which kind of data? Maybe can be determine other functions, not only alpha and beta, only the scalar parameters. Then the answer is like that. We consider one-dimensional fractional diffusion equation. Then initial value will take a very special Dirac delta functions. Then we consider, say, flux or the homogeneous Neumann boundary condition. Then the problem is that we will monitor U0t. Then we would like to determine alpha and p. Then the uniqueness is okay. And since uniqueness is okay, it can be proved. I am presenting. Therefore, more or less, the result is, say, positive. Then the key is Gelfand-Levitan theory for the Sturm-Liouville problem and very classical eigenfunction expansion. I think nothing difficult in a sense. Okay, then recently I am working with my colleagues at the Shandong University of Technology, something like a numerical reconstruction P and alpha on the basis of this problem. Okay, maybe I will skip that. Then finally, sorry, maybe my time management is not correct. Then finally, please let me touch that part because, okay, here, this is a multi-dimensional case. Then we would like to consider determination of the coefficient. Then please notice that previously only results is one-dimensional case. One-dimensional spatial dimension is only one. Then what happens in the multi-dimensional case? That part is a joint work with Professor Luc Miller at the University of Paris-Est. And the alpha can be up to till 2. Namely, alpha, the order of the time, the fractional order derivative is between 0 and 2. Then UP is the solution to our original problem. Like that. If alpha is larger than 1, we must assume also that kind of condition as initial value, initial condition. Then WP is the solution of initial value boundary value problem for the wave equation, namely 2. Then the 2001 Bajulekova proved this kind of transformation. WP is a solution to the wave equation. Then UP is parabolic with a fractional diffusion case. Maybe? Oh, sorry. Then this is a transformation. If alpha equal 1, this is quite well known, like a Laplace transform. Then K alpha is some special function, so-called right function. But anyway, this formula is not so important. But the importance is that we have the transformation formula between the solution UP and WP. WP is the solution of the hyperbolic equation, for which we know quite a lot about the inverse problems. But we don't know about the inverse problem so much for UP. Then the next step is that this can be proved without very big difficulty. Namely, such kind of transformation is injective if we consider the time interval 0 to infinity, because this is a transformation of the function over 0 infinity to other function from 0 to infinity. Then alpha equal 1, again, this corresponds to the injectivity of the Laplace transform. But anyway, then the next is that this is bit I did not mention, but the parabolic, the fractional diffusion equation has analytic property. This is bit rather similar to the analytic semigroup property. Therefore, there is analyticity. Therefore, if the solution, some data vanishes finite time interval, thanks to the analyticity, immediately this must be 0 from 0 to the infinity. Then the circle of the proof is closed because, roughly speaking, then we have proved that kind of result, namely some suitable subdomain omega is like a neighborhood of the whole domain. Then here a priori we must assume P equal Q. Then some also non-negative condition, then if two solutions to the fractional diffusion equation coincide in the subdomain over time interval, we can conclude that P equal Q. And if alpha equal 2 for the hyperbolic equation, this result can be proved about 30 years ago by Russian mathematicians Alexander Bufgame and Mikhail Kribanov. Therefore, thanks to such integral transformation, we can reduce this kind of inverse problem to the hyperbolic coefficient inverse problem. Okay, but I will skip that. Then also maybe some work was done for the determination of the non-linearity under some limited case, but maybe just that part is some joint work. Okay, sorry, I should keep the time for your comfortable lunch time. Then thank you very much. I would like to stop here. Thank you very much for your kind attention.